The lens, the larger it is, the more it increases, because if we assume that I have a photon coming at an angle, a scattered photon, if this lens is short, it's like this. There's a photon here, and if we assume that this photon will pass at this angle, it will go through here. But if it comes at the same angle and hits these long holes, it will collide with them and won't have the space to pass through. Can you imagine? Because the longer the lens, the more it will create a situation for the scattered photon coming at an angle, unlike when it is short. So it might allow a photon to pass through. Therefore, my resolution depends on two things: the diameter of the holes being small and the length of the setup being large. These will improve my resolution and reduce my sensitivity, unlike here. You reduce the lens length, which increased the sensitivity, so it is called high sensitivity energy. This is, of course, because the medium energy of your technique is high. So, what is the idea here? And what I want to say is that you need to optimize between sensitivity and resolution while using a specific type. The calorimeter, a crucial instrument in various scientific examinations, depends on the type of examination you are working on, which is why it has something called low energy all-purpose or general purpose, which provides reasonable resolution while also giving you high sensitivity. It plays a vital role in determining the energy levels and sensitivity required for different types of tests. This is particularly important in fields such as physics and chemistry, where precision and accuracy are paramount. It is about energy and the purpose of the calorimeter that I was talking about. For example, you might find the calorimeters coming to you in the area saying, I have high energy, high resolution, medium energy, and high energy. Also, those with all-purpose have large holes, so their sensitivity is considered higher than low energy, high resolution. Now, what difference does it make if the sensitivity is a bit high? What difference does it make if I increase sensitivity? Do you think it will affect resolution? Yes, resolution will decrease. Now, if my calorimeter allows me to take 1000 counts per minute, and another calorimeter allows me to take only 500 counts per minute, this affects the scan time, which is a very important point. The examination time for your patient to perform a scan requires a certain number of counts to produce an image in the end. If the count is low, the image will be noisy. So you need to achieve a high count to get a good image. Therefore, you need to increase the time significantly to reach your target count that gives you a good result. That's why it was mentioned that the air detection count was 500,000. For each microcurie of the used area, the used area is said to be 1 centimeter for every 10 centimeters of the used area. The used area has the highest used area, about Dubai. It is the highest. From what is known as all-purpose energy, it has more holes, because you have reduced the distance or the diameter. I expect that with a smaller hole diameter, the counts increase, and by increasing the length of the holes, it became more deeper. Okay, I was saying that everything was fine, but it was higher, meaning what? It means that you can work with it between the execution. The execution was higher by 1 centimeter. What does it mean? 1 centimeter means the distance you can use to separate two objects. When I say 0.65, it means the distance you can use to separate two lesions or two hot lesions is 0.6 centimeters, which gives you more resolution. As we said, medium energy is used with gallium, indium, or krypton, while high energy is used with iodine-131 or even FDG, because it gives you 500 kiloelectron volts. Low energy, high resolution is used with technetium. With technetium, that's fine. Now let me show you the shape of the collimator, or the holes in high energy. And here is its shape in low energy. There is something called high resolution and something called ultra high resolution. In ultra high resolution, you'll find that the diameter of the holes becomes much smaller. In reality, we don't see many people using it. But most people work with low energy, high resolution, especially in cardiac cases, or low energy. Of course, medium energy and high energy collimators depend on the type. If we have iodine, we use high energy. If we have gallium or indium, we use medium energy collimators. Here is the low energy collimator, and here is the medium energy, and here is the high energy. The star artifact that I was talking about has disappeared with high energy and is present with low energy. One of the points that affects resolution and sensitivity is distance. As the doctor mentioned, the further away you are, the more you can expect your resolution and sensitivity to decrease. Therefore, you should always try to keep your head, crystal, or collimator as close as possible to the object, as this will reduce something called penumbra. If you remember the topic of penumbra we discussed, if I have a collimator with a borehole like this, and I have an object here being imaged, the object is supposed to be the only field of view I want. However, if you are far from the borehole collimator, a scattering area may form, which is known as the penumbra. If we recall the topic of the I3 tube and remember that I have an object, I said that this is the image receptor for me. Remembering the penumbra topic, I mentioned that with a small focal spot size, a region appears, and this region is called the penumbra, which affects the resolution of the margins. Well, if we remember, from what we were saying, the penumbra region was heavily dependent on the distance between the object and the X-ray tube. This is similar to our discussion about the X-ray tube here. The idea is that the farther you are from the detector, the scattered angle or scattered photon coming from your margins will weaken the resolution of your object, thus increasing the binomial region. If you are closer, the likelihood of the scattered photon passing through these holes and being detected increases. So, distance is a parameter affecting sensitivity and resolution. The same idea applies. The closer you are, the more detection you can achieve for more counts of gamma photons, which enhances your sensitivity. So what else? The things we said we are asking about them. We talked about converging and diverging here. It's like you're doing magnification exactly. The design of the collimator allows you to do this. Currently, the use of converging or diverging, or even the pinhole can be considered the most commonly used. As we mentioned, the holes of the pinhole have an aperture, and this aperture comes in different sizes or different diameters. 3, 4, or 6 millimeter aperture. Different diameters of 3, 4, or 6 millimeters. The aperture is such that whenever you want a high resolution, you reduce the aperture size. This means it has a cover that is removed and installed. For example, if you set it to 3 minutes, you want high resolution. At 4 minutes, the resolution is lower. At 6 minutes, the resolution is even lower than that, and lower than 6 minutes has even less resolution. You tell me about the idea that you are doing to see if there is anything present in a better way. In reality, I don't really see this issue much. So even in our work, as we said, most people are working with what is available and its existing relationships. The 6 hands of thickness and their relation to what is present. And this is also another shape. These are the holes that are present and the thickness. Can you all imagine now the shape of the collimator, the thickness, and the lens? Is that correct? Or are there any issues? The collimator also has a field of view or diameter of about 40 centimeters or 400 millimeters, and the thickness is around 25 millimeters. The count of these holes reaches about 20,000, and they take the shape of either circular or hexagonal holes with a diameter of about 2.5 millimeters. The thickness is about 0.3 millimeters for the gamma absorber that comes with a scattered angle. For example, this illustrates the relationship between the point source when the distance is close to the collimator and here when it is far from the collimator. In the case of being far from the collimator, see what happened, what the difference is. Focus on this together, doctors. Here, the object that appeared in this area has a small dimension because there is no spreading. The angle number here is considered low, unlike here where your angle number is large and spreading has occurred. The size of this object seems to have increased, and this increase has reduced your resolution. There is something called point spread function. We talked about this topic before, but we were saying if I have this in an area that contains a material of feelings or something, and I took something called this, what were we saying? We were saying that I measure every point in this area. What is in this area? I measure every pixel, every point. The count in this area. What is the count? 0 means high or low. It can increase or decrease, right? There is something called fall width at half maximum. What does it express? It expresses the amount of width of my curve. This curve gives something called Gaussian distribution, which is not our concern, but I want to tell you something. The sharper this curve is, the smaller the full width at half maximum will be, which means the resolution is high, right? But if your curve is broad like this, then the full width at half maximum is large, which means your resolution is low. Now let me show you how to calculate the full width at half maximum. I look at the highest point here, which is the peak. For example, if I have 100, what is half of that? I have 50, and I take a projection like this. I say this is x, and this is y. x2, x1 means delta x over y. I'm sorry, not over y, but over the highest value over the maximum for me. I'm sorry, not over y, but over the highest value over the maximum for me. It expresses that the عرض النطاق الكامل عند نصف الحد الأقصى indicates your resolution. The عرض النطاق الكامل عند نصف الحد الأقصى represents the width of the curve. The smaller this width, the lower the quantity of the عرض النطاق الكامل عند نصف الحد الأقصى, because the difference between x2 and x1 will be small, resulting in a narrower width and higher resolution. This is determined based on the object you are observing. Look at the margin spread in this way. If you look at this first image, if you take a line profile, you can compare this image at 0 centimeters with an image at 30 centimeters. If we look closely, you can see which image has better margins. The margin of the circle of the object is better at 30 centimeters. Therefore, the image of the object that is closer has clearer margins, resulting in better resolution. The curve representing the point spread function is sharper, and the عرض النطاق الكامل عند نصف الحد الأقصى is lower, leading to higher resolution. So, as long as you have the crystal or your collimator, you reduce the penumbra, which increases and decreases for you, and this is very important in the process. All right, doctors, this point is clear. Now we talked about the collimator. Let's talk about how the photon, thank God, has passed from the collimator and is now going to enter the crystal. We mentioned before that I cannot directly use the X-ray photon or the gamma ray photon. It must be converted into something. This something should give me a large number of light photons from the X-ray or gamma ray if there is input, and I want to convert it into a large number of light photons to increase intensity so that I can work with this signal and produce an image. So the light photon that entered has now been converted into 5,000 light photons. How did this happen? It entered and interacted with the scintillator crystal or sodium iodide, which is against the material of the sodium, with a thickness ranging from 6 to 13 millimeters. Its diameter is 500 millimeters, about 50 centimeters. And it produces light photons that emit in all directions, meaning they can go this way, that way, and come back. Some of them may experience backscattering. Around 4,000 light photons undergo backscattering. The process that occurs is called scintillation. What does scintillation mean? Here comes the Eshat Jama photon. When an electron comes into contact with the scintillator material, it is forcefully knocked out of its orbit. This scintillator material has properties such as those that allow it to emit something, and as it returns, it gives you back a signal. For example, you have the light photon. This light photon I receive on a specific light guide, and then I connect it to the photomultiplier tube. I connect it to the photocathode of the photomultiplier tube so that it converts to an electron. After that, I perform multiplication on this electron inside the photomultiplier tube and convert your signal. But let's just talk about something. All right, let's put this. Now after this, there is a count from the collimator that happened here. This resulted in photons reaching the photocathode. I currently have, for example, scintillation. This scintillation produced light photons, and these light photons reached the photocathode. I have several photomultiplier tubes here. 1, 2, 3, 4, 5 photomultiplier tubes on the surface of the photomultiplier tube. Here, at the photocathode receives the light photons and converts them into electrons. The electrons enter the photomultiplier tube and undergo multiplication. So, this is the photocathode that absorbs the light and produces electrons. For every 5 or 10 light photons, you get 1 electron. Now, let's look at the multiplication. Here, 140 kilo electron volts entered the crystal, producing 5,000 scintillation photons that traveled through the light guide and entered the photocathode. The photocathode converted them into electrons, resulting in 300 photoelectrons created at the photocathode, meaning it transformed solid colors, ultimately reaching 300 photoelectrons at the photocathode. Inside a photomultiplier tube, the photomultiplier tube is a vacuum chamber because air would hinder the movement of electrons, as we discussed earlier. It is connected to something called dynodies, which have an increasing volt. What does increasing volt mean? It means that the voltage here is higher than before. This voltage provides kinetic energy because the transition of an electron from a low voltage to a high voltage gains kinetic energy. This kinetic energy allows the electron to collide with the dynode, producing 2 or 3 more electrons, which then enter the new dynode. Each of these produces 2 or 3 more electrons, so you are essentially performing a multiplication process until you reach the signal at something called the anode. The anode is the last stage in the photocathode. After that, you start converting this signal into a volt signal, into a pulse signal. All of this is the photon that just entered from the collimator. Now let's see this. Here is the shape of the photon, everyone. This is what it looks like when we open the back of the head. So here is our head. Do you see this head? The open collimator is placed here in this area. This is head 1, and this is head 2. This camera consists of a pair of heads. This view from above shows the shape of the photomultiplier tubes, which can sometimes reach up to 90 photomultiplier tubes. All the photomultiplier tubes are arranged on the crystal, meaning they are placed above your crystal. So can you imagine that the crystal is above the photomultiplier tubes? The photomultiplier tubes are arranged like this. Look here. This is the multiplication that occurs when light photons hit the photocathode and are converted into photoelectrons. The photoelectrons then start to work and undergo multiplication in this way. Great. Add dinodes plus, and multiplication occurs until it reaches the final anode. And this is the actual shape of the photomultiplier tube. This is the main electron that is inside, and the second electron has transformed into it. It has a preamplifier that, as we said, receives the incoming signal and converts it into a volt pulse. After that, the volt pulse begins to undergo processing, entering something called the XY positioning circuit, and then into something called the pulse height analyzer. We will discuss this in a moment. And we will also introduce something called the bulk site analyzer, which we will talk about now. Okay, so my journey started with a gamma photon. This gamma photon came from the source, passed through the kilometer, entered the hole, and created a photon like this. It reached the photocathode, which converted it into a photoelectron. The photoelectron then entered the photomultiplier tube, where it underwent multiplication and produced a signal. The question is about the patient. If I assume that I have an element like the technician who emits energy of 140 kV, can this photon interact inside the patient's body or not? Are you all tired or what? Are you doctors tired? Just a little. I mean, so do you understand, or are you completely lost? If you're lost, why is that? But if we can continue a bit, there's no problem, because I have to rely on you. Thank God we understand. The important thing is that we understand, which is good in itself. Thank God. All right, look, doctors, the material in the patient's body undergoes interactions. We talked before about the interactions that can occur between the photon and the material or tissues. We discussed a type called the photoelectric effect and another type called Compton. Do you remember this? The photoelectric effect is an interaction that occurs between the photon and the K-shell electron. So, I have an atom with a nucleus, and around it are the K and L shells, which contain electrons. If the photon is fortunate enough to create this electron from its orbit, this electron is called a photoelectron. It receives all the energy of the photon, so the photoelectron exits with all the energy of the photon, and the photon disappears. This is called the photoelectric effect. If this interaction occurs in the patient's body, will the photon have an effect or presence? No. It will be absorbed in the patient's body, right? Did I say something wrong? All right, so this is the first photon that unfortunately got stuck with the patient's body and won't reach the crystal or even exit the patient's body. Now, a second photon was lucky and managed to pass through. Its energy is 140 keV. Then a third photon underwent Compton scattering. What does Compton mean? It means it interacted with an outer shell electron, knocking it out and giving it energy, while the photon itself underwent scattering. So I called it a scattered photon. Now this scattered photon might pass through the patient's body, right? We said it was cotton, but its energy will be lower, not 140. It will definitely be less because it gave part of its energy to the electron. So, it has some energy left, right? Now, I want to tell you that what will reach the crystal could either be the 140 keV photon or a scattered photon with energy less than 140 keV, right? So, we understand what is coming out of the patient and heading to the crystal. All right, doctors. Great.